Hello! Welcome back to the first lecture in the Renewable Energy Technology course on wind turbines and wind power. We are still at the basic aerodynamics, major types and operational principles topics, and we have reached the last section of this lecture where we will quickly make a review on the power output regulation methods and control mechanisms for wind turbines in the real world. First and foremost, a wind turbine never operates at its output or nominal rated output. Well, not really never, but let's say seldom. Or definitely for most of the time, a turbine or the turbine will operate at part load. This is easy to understand, and please remember it. This is the major issue when it comes to actually deploying wind turbines. You invest in something that operates just part of the time. And how exactly it operates depends very much on the wind. If there is no wind, the turbine wouldn't operate. It's quite stochastic, the wind is difficult to predict, and the machine needs to be very responsive and very efficient in the entire spectrum of wind turbine speeds. If there are low winds, the turbine would deliver somehow low power output. This is clear. And it's actually most of the time that this happens. At very high winds, there is a lot of energy in the wind, and it would be nice if we could efficiently use it, convert it, deliver it. However, high winds, good energy winds, they don't happen very often. Actually, they occur quite seldom. And the wind turbine doesn't need to be dimensioned, built, rated for the high winds. We would rather need to dimension it for somewhat average, most prevailing winds or wind speeds. At very, very strong winds, say storms, there is absolutely no good idea to try to convert the energy in the wind. It's enormous amount of energy hidden in the wind. Remember, it's the cube of the wind speed that gives the energy of the wind. So the primary target at storm winds is to preserve, save the machine. Save the investment. Don't let it topple down or fly away with the wind. So the turbine is entirely stopped. As soon as the wind goes over a certain predefined wind speed, and usually that is wind speed between 24, 25, 26 meters per second, which is exactly the definition of storm wind, you stop the machine. You don't extract any energy from those winds. You cut off the turbine completely. So there are several major points. The cut-in wind speed depends on how optimal or how good optimized the machine is, at which low wind speed it will be able to produce any power at all. Then the rated output, which is the nominal decided maximum possible power that the machine can deliver, and it will need to stay at that rated output as precise as possible whenever the wind is stronger than the nominal rated wind speed. At very strong winds, cut off the machine and save it. This is a pathetic attempt here to represent the actual available energy in the wind, but you get the bottom line. Actually, it is a function of the cube of the wind speed. So the wind turbine never at any position is able really to convert all the available energy. It converts part of it. And the more we go towards rising or growing wind speeds, the lesser efficient the machine will be. When the energy available in the wind goes through the roof here, we will need to dump lots of power really so that our machine produces the maximum that it's dimensioned for, but absolutely not possible at all to approach the really available power in the wind. There is something else, and it belongs to other lectures. We don't have time here now to talk about the grid connection issues, but it will be mentioned by another teacher, and we will mention it shortly in the next lecture. The point is that as soon as you connect a turbine to the electrical grid, regardless of how big the turbine is, as soon as the grid is big enough so that you actually connect a typical electrical generator into a large pool of other electrical generators, the grid completely controls the machine. It depends a bit how the turbine is constructed, what kind of electrical generator it has, and what kind of connection infrastructure it uses. If it is a simple electrical generator directly connected to the grid will completely hold it, control it. The frequency would be the same. As long as you are connected to the grid, you cannot do anything with the frequency of rotation of the electrical generator. It will be approximately the same. Now again, it depends what exactly type of generator we talk about. Again, we don't have time now to explain these things, but assumingly you know them already, so please remember, the grid plays a vital role into how the turbine behaves. And this comes back into the aerodynamics, and of course also the mechanical engineering and loading of the turbine. All large utility scale machines and wind parks, of course, the turbines are connected to the grid. Whether directly, depending on the type of generator, or through some power electronics, the grid still exerts some influence on the machine. And how exactly you control the turbine to follow its proper power output curve, it is dependent on how it is constructed both mechanically and electrically. And backwards, it influences its aerodynamic performance. So direct connection or indirect connection, whatever stays here in between the machine and the grid, there will always be a transformer, but there might be also power electronics completely disconnecting virtually the machine from the grid. Or if it's a direct connection where the frequency is fixed and the turbine cannot do anything, cannot run at any changing frequency, power output, yes, but not RPMs of the rotor in this perspective, as soon as it is connected to the grid. To change anything, you have to disconnect it. All these issues are very, very, very primary when understanding how the machine works. We are skipping them now, but let's move further and actually talk about what the targets are. The ideal control for the wind turbine would need to be very effective in the low wind spectrum. Cut in speed as low as possible, go up in performance as quickly as possible, keep the rated output as precise as possible without overheating the machine but without also losing power, cutting off in a somewhat soft way the machine from performing when the winds are too strong, not abruptly but preferably in somewhat soft way. Still, if there are strong winds, if you are able to use or convert as much energy as possible, that would be nice. At least nice for the return on investment. But you're not supposed to read everything on the slides now, and I am not going through all the text, but please, you will have those slides available. Look at them. The text is very carefully selected to properly say exactly what needs to be defined. Let's quickly go through it. Now, ideal control system should allow the rotor to operate with maximum efficiency at low winds. Absolutely important. Then, it should very effectively limit the power output at wind speeds above nominal. Very important again. Then it should effectively again stop the machine at strong storm winds, but preferably with a soft stop and start option. It's not really soft in reality, but if it were possible, that would be perfect. The output regulation indeed is achieved by simply decreasing the aerodynamic performance. Or this means that a variation of the power coefficient is attempted. Destroy the efficiency of the wind rotor when you need to cut off or simply to regulate the power output. First, allow it to spin up or to increase power output at low winds as effectively as possible. Then control it and decrease the aerodynamic performance again as efficiently as possible in order to keep the rated power. the turbine is not able to deliver anything more than the rated power. And you're not playing games with it. It is a multi-million investment. Two types of output regulations: stall and pitch. Now let's talk about stall and pitch. You have heard those words. You have to translate them now into fluid dynamics perspective. Stall can mean different things. In the world of fluid dynamics, stall is used to define the turbulent flow behind the wind profile. There are many applications where stall can be used or misused. It is very detrimental for an airplane if the wings, for example, start to stall. It will fall down. In the wind turbine, it is possible really to play with stall and use it exactly to decrease the aerodynamic performance. Use it as a brake. Stall occurs at very large angles of attack. Whatever the flow, whatever the fluid, whatever the wing profile, if you increase the angle of attack, actually the flow would start separating at the suction pressure of the wing profile. First slowly towards the end, and if you continue increasing the angle of attack, so actually the apparent wind approaching the blade more and more towards the belly or the pressure side of the blade, the more or the sooner the flow would separate behind the blade. The more turbulence, the more swirling vortex behind the blade, the worse the aerodynamic performance is. So actually you're dumping literally the power coefficient or the effectiveness of the wind rotor. How can stall work at all? It actually works only for directly connected turbines to the grid. These are the simplest, the most robust machines, which primarily used simple induction generators in the early days of wind turbine technology. The good thing is that the blades are firmly fixed to the hub. The rotor is completely controlled by the grid. It actually travels at the same speed. So this vector here represents the translational speed of this section of the blade. And even if this actually drawing might not be the best one, it actually shows the situation in the best way. So this is the axis of rotation, imaginary. We're looking along the axis of the blade, cutting it at a section. And all sections of it, whatever happens with the output, actually they travel through the air with the same translational speed. What changes is only the velocity of the undisturbed wind, which alters the velocity triangle, meaning it alters the angle of attack. Whatever the power output, the rotor is rotating with the same RPMs. Thanks to the fact that it's directly connected to the grid with a simple induction electrical generator, and it cannot change RPM. The stall regulation power curve suffers from two basic disadvantages. First of all, you're losing too much performance in the high wind spectrum. It is not really possible to predefine the position of the wings, of the blades, in such a way that they perform perfectly and keep a stable power output. Actually, what happens is that the blades perform worse and worse towards the very, very, very strong winds. And until you reach your cutoff wind speed, typically 25 meters per second, you actually have lost quite a bit of undesired losses of efficiency. Also, the low wind spectrum may not be as optimum as it could have been with a better or somehow actively regulated angles of attack. The merits of the stall regulation, and that's why it was actually selected as the primary option in the early days in the first generation wind turbines, is simplicity and robustness. Very important, which also bring cost effectiveness. Early machines, they were comparatively simple per unit installed power, thanks to using simple components, simple arrangements. The blades firmly bolted to the hub rotates, or the whole rotor rotates at stable RPM, really easy. If the rotor were not rotating at stable RPM, this situation wouldn't be possible. And if the rotor would be more effective, it has to have a certain window of variable RPMs. So that's how people define the pitch regulation, and it is definitely the regulation of choice for modern machines. All big turbines now prefer pitching instead of using stall. Plus that actually stall is a bit dangerous because it increases the loads on the machine enormously. Pitch as a term also comes from various applications. In the turbine world, it usually means the distance between two blades. And as soon as you start feathering those blades, actually you change the distance in between them. So pitching of the rotor blades would mean that you rotate the blades, you flip them, literally, along their own axis. In fluid dynamics, this means that you might be able to sustain the same angle of attack, whatever the change in wind speed is. Now, exactly the same situation here, exactly the same wind speeds used as an example. Again, for the good example, the rotor is traveling with the same RPMs. Say it's again a simple electrical generator directly connected to the grid. What is changing is the wind speed. Again, changing the velocity triangle, the actual velocity triangle that the blade experiences. But the blade pitches to follow the wind. When the apparent wind travels like this and turns more and more towards the belly of the blade actually pitches continuously and follows the vector, keeping the angle of attack, say, ideally the same. What the difficult part here is that you have to be able to rotate this blade. You need to have a complex mechanical arrangement able to do that. Some kind of a control system, some kind of an actuation system, motors able to rotate the blade, bearings that this blade is supported on. It cannot be just firmly bolted to the hub. But the achievements are wonderful. Pitching, or the pitch regulation, is able to deliver very nice performance in the low wind spectrum. You can start pitching already from the cut-in speed, and then you're able to support and sustain a very nicely stable power output in the high wind spectrum. You can also play, if you would like, also with the cut-off speed pitches. If as soon as the blade can pitch, it allows to do everything. A major drawback, again, is the complicated mechanical arrangement. This translates into not only high costs, but maybe components that may break down, demanding higher maintenance expenditures and decreasing the reliability, availability of the machine. If this helps for the better understanding of pitch and stall, we can use this common diagram saying that actually in optimum performance, the turbine is attempting to operate always approximately in this range here. Angle of attack defined so that the lift coefficient towards drag coefficient is as big as possible. The stall would attempt to destroy lift by going towards large angles of attack, creating enormous drag while continuously losing lift. Ideally, you can go to infinity here or to 90 degrees, where you have no lift and full drag. This would effectively just stop the machine. The pitch regulation would attempt actually to keep low angles of attack and then decrease the lift, going towards the zero angle of attack if necessary, and mechanically the turbine should be able to do that. This is the way to stop it, while drag is also maintained low. So you do not produce enormous thrust load pushing the machine. Active stall regulation is also an option, and it was, only one wind turbine manufacturer was using it in the old days. It was developed to combine the positive effects of pitch and stall while hopefully avoiding the negative effects of both pitch and stall. Active stall would mean, well, compared to passive stall, where the blades are firmly bolted, that you do have pitch components and options for pitching of the blade. but you do not pitch it in the way that the pitch regulation would demand. You pitch the blade in stall direction. So it is possible to optimize the blade in such a way, fit it on the hub, that it is better fitted, better optimized for the low wind speeds, for example. And then at high winds, it is not really passively stalling in the best way, so you help it, you actively pitch it to stall properly. This is a nice representation of a comparison between pitch and stall. If you would pitching the blade, you need to turn, actually, you need to have a large spectrum of possibilities to flip the blade. And then you would increase the angle or follow the wind as much as possible towards the 90-degree angle if necessary. If you would be stalling the blade, you don't need to have such a large spectrum of pitching. You need only a few degrees. They are enough to deliver the stall. Remember, the stall is turbulence behind the blade. The blade is already defined from the very beginning. It is fixed in such a way that it produces some stall. You simply aid it additionally with a few degrees in the other direction, just to produce the proper amount of stall. And this is how, the opposite direction exactly, you would be flipping the blade, only a few degrees. The active stall power curve, well, it aims at delivering nice, very, very well-maintained output, rated output at high winds, also nice and optimum power output at low winds, and avoiding some of the drawbacks of stall. There is one very hidden drawback of stall. That's actually the reason for the active stall to be developed, even if it's not really used, especially not nowadays with the big turbines. It is pretty much an aeroelastic phenomenon. It is easy to understand, very difficult to put in equations, and we're not going to do that here. The point is just the fundamental understanding. And, well, think about the typical stall control. The blade travels with the same speed, the angle of attack changes, stall appears behind. Fine. The position of the blade doesn't change. It is firmly fixed to the hub. The stall control, or the stall phenomena, really increases the loads on the machine while dumping aerodynamic efficiency. That dumping action represents itself by larger forces just pushing the turbine. If there is a fluctuation in the wind speed, and there always are fluctuations, the wind is never super stable, those fluctuations will be fluctuating or varying force only in the thrust direction, pushing the turbine. But with pitch, now if there are fluctuations in wind, they would immediately occur in the same direction that the blade is rotating to. So those fluctuations, even if much smaller loads, not really pushing, no thrust on the machine, at least not so big, they would be fluctuations in torque. So the rotor performance will be jerky. This immediately goes into the electrical generator, ending up as fluctuations in the output power. It can really be serious. So the early pitch-controlled machines, they had a problem of taking care of those fluctuations. Different methods can be used to dampen or eliminate almost completely the pitch control related fluctuations, where the wind or stochastic wind speed or short-term fluctuations in wind actually immediately appear as fluctuations in the output power quality. The stall is a kind of a self-feedbacked control method. It is really good in a way that you do not need to exercise or to execute an action. You don't need a signal and then actuate a system to regulate anything. It is pretty much self-regulating. As soon as the angle of attack starts to change, the stall appears and the blade is self-regulating. With a pitch control, of course, you do not only need to have those mechanical arrangement so the blade can flip, you also need to have a proper control system where the feedback problem, and you remember what a feedback problem is in the control theory, you have actually to have a change so that you detect, send the signal before your control system manages to act. Pitch control, therefore, is always a bit slow, and you cannot make it quick enough. And if there is a constant variation in wind, your blade will start crazily flipping all the time. These things need to be handled, first of all, by the control system, and second, by various other both aeromechanical and purely mechanical arrangements, which are not the topic of this lecture. Simple comparison between pitch and stall. In the old days, stall was the primary choice. Pitch control more and more started to take over, and now this definitely is outdated, but I tried to explain here very easily what happens these days towards modern time. Pitch control is completely the governing choice for all big machines. There are very, very few stall-controlled machines, mostly small, and nearly zero active stall-controlled machines available on the market. However, many of those early designs, they are still operational. Some of them accumulated more than 20 years of almost trouble-free operation. Quick summary. Both pitch and stall, purely aerodynamic concepts for maintaining the rated power output at high winds, using the fact that the aerodynamic performance of the rotor can easily be destroyed by changing the angle of attack. Both pitch and stall have advantages and drawbacks, of course. And the relation to induced forces and vibrations can be actually the most serious disadvantage for one or the other control method. Most early commercial turbines were stall controlled. Simple, robust, low cost. Almost all modern big, large machines are pitch controlled. We need pitch now to be able to properly regulate the rotor, to be performing at the optimum level, both at low wind speeds, high wind speeds, and of course, to deliver maximum performance for the investment. Thank you, and this is the end for the first lecture. We will move on with the second lecture on mechanical construction of wind turbines.